In section 13.3 and 13.4, we're going to talk about contingency tables and association. The idea here is that we're going to say we go up to 40 students and we say, what's your political party and what's your class level? And then we record Democrat, Republican, or other, and then their class level, freshman, sophomore, junior, senior. Since we've asked them for two pieces of information, we have two variables. This is called bivariate data. And you can imagine a scenario where we ask for more information, in which case you will get multivariate data, but we're just going to stick to talking about bivariate data in this section. And what you could do is you could summarize all this data using a contingency table. So you could put one variable on for the rows and one variable for the columns, and then you could just record the number that go in each box, in each cell. If you were to divide each of these numbers by the total sample size, which is 40, we would end up with what's called a conditional distribution. Okay, and so this is an object that we've already seen in chapter 4 when we introduced the idea of conditional probability. At the time, we called them joint probability distributions. They go by two names. Okay, so it's a conditional distribution or a joint probability distribution. They're the same thing. One final way that you could summarize this data is with a bar graph. So you could take the data and you could make a bar graph, segmented bar graph like this, where you would have one variable be the different bars, and then the bars could have different segments which would represent the other variable. Okay, so we're going to mostly focus in this chapter. The relevance to the chi-square distribution is going to mostly focus on this contingency table form of storing the data. We're going to say that two variables are associated if the conditional distributions of one variable given the other are not identical. There's a little bit to unpack there. Okay, so two variables are associated if the conditional distributions of one variable given the other are not identical. This has the feel of independent events, but I want to just go back and look at our contingency table. In chapter 4, you could talk about, is being a Democrat and is being a senior, are those independent events? And you could go through and you could plug in the formula. This is a chapter 4 problem. I asked you things like this on the first exam. I have full confidence, so you could go through and answer this. That is not exactly what we're asking. We're not talking about these individual events of being a Democrat or being a junior. We're talking about the variables. Are the variables associated? Okay, so this is somehow a bigger picture view of independence or not. So again, let me say it just one more time. Two variables are associated if the conditional distributions of one variable given the other are different. Okay, if the variables are independent, that means that the conditional distributions of one variable given the other are identical. They're the same. Okay, so if the conditional distribution of one variable given the other are different, then they're associated. If the conditional distribution of one variable given the other are identical, if they're the same, then they're independent. Okay, and so this is the idea to talk about variables being associated or independent. And what we can do is we can run a chi-squared test to determine whether or not two variables are independent. So again, with this idea of inferential statistics, you have some sample. You want to know, what does that tell us about the underlying populations? Are the underlying populations associated or not? That's what the chi-squared test is going to do. And so this is going to be a hypothesis test that we can run to determine whether or not two variables are associated. So this is called the chi-squared independence test. Now, this is going to have the same formula that we had for the goodness of fit test. So chi-squared is going to be the sum of the observed minus the expected squared divided by the expecteds. And you add all those up over all the different values. The thing here is that this is going to be slightly different in that before we had a column, basically a column with one row. So you could think of it kind of as a vector or a list of values just with one row. Here we're going to have a table. And so we need to change two things. The first thing that we're going to change is the degrees of freedom. And the degrees of freedom is going to be the number of rows minus 1 times the number of columns minus 1. So if we go back to our contingency table, we had, let's see, 4 columns in 3 rows. So that means that we would have 2 by 3 for our degrees of freedom. So this would have 6 degrees of freedom. Okay, I'll write all this nicely soon, but we'd have 6 degrees of freedom. The other thing that's going to be different is how you compute the expected value. So what you do is you start with this contingency table, and then to compute the expected value, what you'll do is you'll take, let's say I wanted to compute the expected value for the expected number of Republican sophomores that we will get. And what you do is you multiply 15, so the column total, by the row total, divided by 40. And so the expected value would be 15 times 18 over 40. And then whatever that is, that would be the expected value that you would get for this cell. Okay, so that would be the expected value for that cell of Republican sophomores. Okay, so that's how that works. So this again is just summarized that the expected value is going to be the row total times the column total divided by the size of the sample. And our degrees of freedom is r minus 1 times c minus 1, where r and c represent the number of rows and columns respectively. Okay. In this case, our null hypothesis is always going to be that the variables are not associated. So I always just heuristically, I like to think of the null hypothesis as nothing happens, right? So there's no reason ahead of time to think that any two things are associated. But if there's enough evidence that they're associated, then we'll say that they are. So the null hypothesis is that they're not associated. The alternative hypothesis is that they are associated. Okay, and so again, you can use the critical value or the p-value approach, whichever you like. So what I want to do for the rest of this video is just very simply answer the question, given the scenario that we started with of the 40 students and the political parties and the class academic levels, are the students' class levels and the political parties associated? And I forgot to say, let's just assume that this is at the 5% significance level. Okay, so I forgot to give you a significance level. It should be 5%. So I want to know, are they associated? And there's two different ways that we can do this. The first way is just by hand. And so what you do, again, is if you want to take, so in this case, what I have is I'm computing the expected value for this cell. And what you do is you multiply 12 by 18 and you divide by 40. Okay, and that's how you would get the expected number there. So let's do that. So 12 times 18 divided by 40 would be 5.4. And so we would put a 5.4 there. So this is a little bit labor intensive here, but we do this for each of the 12 cells. Okay, and what we do is we end up with these numbers. Okay, so these are in red, these are the expected values. So again, the expected value you get by multiplying the row column by the row total by the column total divided by the sample size. Okay, and then what you're going to do is you're going to just apply the same formula. So chi-squared is going to be the observed minus the expected. Remember that the blue is the observed. Let me just write this first. So this is the sum of the observed minus the expected squared divided by the expected. Okay, and so the red numbers are going to be the expected values. The numbers that you actually get, the 1, 4, 5, 3 numbers, those are the observed numbers. Those are the numbers that you actually get from the sample, the ones that you observe from the sample. So with that being said, what we're going to do is we're going to plug everything in. We're going to compute our chi-squared statistic. And so you end up with 1 minus 1.95 squared divided by 1.95 plus 4 minus 4.875 squared divided by 4.875. And you do this for all 12 values, all the way up to 2 minus 1.575 squared over 1.575. And it turns out that you end up with a chi-squared value of 3.0818. Okay, so if you do this for all 12 values, this is what you get. Okay, so 3.0818. And then what we have to decide is we're going to look at the chi-squared table. Okay, so we'll look at a chi-squared table. And if we do that, what we have to figure out is what is our critical value. And so if we have chi-squared, we want a statistical value of 0.5. We have 6 degrees of freedom. Okay, and so the chi-squared value, let me make sure I did this right, the chi-squared value should be 1.63. Okay, 1.63. No, excuse me. The chi-squared value should be 12.59. So the critical value, is 12.59159. I think it'd be worth just me pulling up a chi-squared table to show you what just happened, why I have a slight mistake there. Okay, so I'm going to pull up a chi-squared table, and this is the chi-squared table that I linked to, or one like it. Okay, so chi-squared table.net. Okay, and then what we're going to do, let me share my screen with you here. There we go. So what we're going to do is we're going to look at our chi-squared table. And then we have 6 degrees of freedom. And we want, we were looking for the 0.05 significance level. So that's what P is. So that's 12.592. I had incorrectly thought about 0.95. So just using R, I used a different value. It's not even on this table actually. But 0.05 is our critical value. So let's go back and let's look at the hypothesis test that we had run before. And so let's compare our values there. Okay, and so we have 12.595. Our test statistic was 3.0818. And so what's going to happen, I think this is again just worth drawing a picture, but we have the chi-squared distribution. We have a cutoff, a critical value of 12.59. Our test statistic was 3.08. Okay, and so we fail to reject the null hypothesis. Okay, in other words, this sample gave no evidence of association at the 5% level. Okay, the last thing I want to do in this video is to show you how to use R to solve the same problem. Okay, so let me show you R. And there's a few different things that I want to show you here. There's a few different things I want to show you with R. This, by the way, is the mistake I was making. I wanted the 0.95 confidence, so 0.05 significance, and that gives us our cutoff there. But let me go ahead and show you how to do our data. So what I'm going to do is I'm going to go back up to our contingency table, which I have on the iPad, which admittedly you cannot see right now. But I'm going to look at the contingency table, and I'm going to record that there were 1 freshman, 4 sophomore, 5 junior, and 3 senior Democrats. For the Republicans, the count was 4, 8, 4, 2. And for the others, it was 1, 3, 3, 2. And so I always just like to double check the numbers, make sure I didn't make any silly mistakes. And there we go. And if you add up all of these, the Dems, the Republicans, and the others, this is just another thing that you can do to double check that you didn't miss anything. It should get 40. Okay, so it looks like everything is fine. What I'm going to do is we're going to form our matrix, and I'm going to call this matrix M. Call it whatever you want. Call it Fred if you feel like it. But the matrix I'm just going to call M. And what you're going to do for a matrix is, I'm just going to use the code matrix. And then what you're going to do is you're going to put the data here. And I could put 1, 4, 5, 3, 4, 8, and so on. But what I'm actually going to do is I'm going to look at the Dems, the Republicans, and the other. So those are going to be my categories. And let me just mention what that's going to do, just this code by itself. So remember that when you're concatenating, if you were to have, say, a list of 4 numbers and y is a list of 2 more, then when you can concatenate 2 lists, you're just putting them together. You got 1, 2, 3, 4, 5, 6, you're putting them together. So if I were to concatenate the Dems, the Republicans, and the others, this will give you all the data that we have. Oops, I call it other, not others. So let's do that again. And that'll give you all the data that we had in our table. So that's how I'm going to store it there. So I'm going to let M be the matrix with that data. So Dem, Republican, other. The number of rows that we're going to have, let's see, we're going to have 1, 2, 3 rows. We're going to have 4 columns. And if you don't put anything, the way that R is going to store the data is by filling the columns first. So it's going to fill, starting in the top left, fill the first column and then move over to the second column. But that's not how I've organized the data. So I'm going to have it sort by row. And if you don't put anything, it has this by row option being false, meaning that it'll sort by columns. But if you put by row equals true, then it'll sort by row. Okay, and then that's it. That'll give you M. And there's your matrix with those numbers. A matrix, again, just being an array or a table, however you want to think about it. And so that's how you can store the data. But the way to run this test is to run a chi-squared test with the matrix M at the 5%, oops, and I forgot the dot test, at the 5% level. Our correction term, we're going to turn off. So the correction term will be false. And we don't need anything else. So we have our data there. And there we have, so you can see our degrees of freedom is 6. We have a chi-squared value of 3.08, which is what we computed before. Our p-value is 0.8. So again, that p-value being bigger than 0.05 tells you that you failed to reject the null hypothesis. Okay, and that's it. So this is Pearson's chi-squared test using R. The last thing I want to do just to show you how this works is I want to show you how to use R just to find the expected values. I don't know why you would want to ever use R to find the expected values, but not run the chi-squared test itself. But just in case you wanted to verify those numbers for yourself, you can use what's called the outer product. And there's a little bit of linear algebra here, but the outer product essentially will compute the expected values. If you type in, so first you'll type in what represents the rows, which is in our case, the party affiliation. So what I did is I stored the party sums. So these are the row totals, 13, 18, and 9. And then the column totals, 6, 15, 12, and 7. And what you do is you take the outer product of the party with the class. And what that'll do is that'll take the row total times the column total for each of those values and plug them in. And then you're going to divide by 40 to get the expected values. So these are the different expected values that you computed for each of the different cells that you had in the contingency table. Okay, so again, just for what it's worth, just in case you would ever want to do that, that's how you can